The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Settle down. Settle down. Settle down. All right, first announcement is the celebration of learning, reminding you celebration of learning, week from today. Week from today. Go to your assigned rooms. A through HA will write in here. This group will go into 26100 and the last group over to 4270. And you will take with you your periodic table, table of constants, aid sheet, something to write with. And we'll give you paper you'll write on the exam paper itself. And I'll say more about test-taking strategies on Monday. Coverage will be right up through Monday, with emphasis, obviously, on the material that you've had some time to digest. And there'll be no weekly quiz next week. So let's get right into the lesson. Last day we looked at Lewis, who gave us the notion of achieving octet stability by electron sharing. And that led to the concept of covalent bond. And then Pauli helped us understand the energetics of covalent bonding by putting forth the idea in a heteronuclear molecule there's unequal sharing of the electrons. And out of that emerged the concept of polar covalency and the definition of electronegativity. And this is the on the slide, you see how electronegativity varies across the periodic table, electronegativity being a measure of the pull an atom has for electrons within a covalent bond. And as you would expect, the nonmetals, which are good electron acceptors, are also the ones that have the highest electronegativity. And the metals over here, which are good electron donors, are those that have the lowest value of electronegativity. And Pauli was quantitative in his formulation and gave us this equation that tells us how to measure the energy of the XY covalent bond. If X is not equal to Y, then axiomatically this is going to be a polar covalent bond. And you take the geometric mean of the homonuclear bond energies. This is XX bond energy in X2. This is the YY bond energy in Y2. You take the product square root of which. And then the partial ionic character, this is the contribution to unequal sharing of the electrons. You take the square of the difference in the electronegativities of the two elements, and the 96.3 is a factor that allows you to get the overall quantity in kilojoules per mole. So you need these numbers in kilojoules per mole. And we further had a formula for the percent ionic character, which you can get by looking at the difference in electronegativity. And then through this formula, you end up with a scale that runs from 0 to 100%. And just by way of example, we had a look at HF. We spent a fair bit of time on that. Obviously, it's a heteronuclear molecule. We calculated its bond energy and so on. And then to indicate polar covalency, we used the dipole notation. The dipole is shown here. It's just an oval. It's net neutral. But the charge is not uniformly distributed. You see one end is a little more negative, and the other end's a little more positive. Sometimes people write lowercase Greek delta, indicating little bit negative here, a little bit positive here. Net neutral, there's the arrow indicating the dipole. And furthermore, we argue that this is it's a polar bond. It's a polar bond, and since this is just a molecule with the two atoms, then this is also a polar molecule, which means it has a net dipole moment. Net dipole moment, and I made some observations about dipole moments and the ability to store energy capacitively and how you'd go about finding a really good capacitor. And so that all came out of the desire to find something that has a net dipole moment. And I want to continue that conversation, and so I want to look at some other elements some other elements. And what I want to look at in particular is the compound methane. Let's look at methane from this newfound appreciation of polar covalency. So first thing I want to do is to put its structure up. We know we've gone through the Lewis notation and the structure. It forms sp3 hybrids, and you end up with a structure that looks like this. These are all at 109 degrees, symmetrically disposed in space. And we know since we have a heteronuclear system here, we're going to have some polar covalency. And you can look up that the electronegativity of carbon is 2.55. Electronegativity of hydrogen is less than that from its position in the periodic table, but to be quantitative, it's 2.2. So that means if I look at the carbon-hydrogen bond, carbon has the higher electronegativity, so it's going to pull the electrons. So that means that the carbon end is going to be a little bit negative, and the hydrogen end is going to be a little bit positive, so that means I've got a dipole moment here, polar bond. Polar bond. Everything the same as above here, polar bond, but I want to address the question, molecule. Is the molecule polar? So the way I understand the question, or the way I interpret the question, is that a polar molecule, I ask, is there a net charge displacement? Well, we're off to a good start here. We see that we have charge displacement on the bonds, but is there a net dipole for the molecule? So the way I think about that is to say, where is the center of positive charge for the molecule? Where is the center of negative charge? So I know all of the hydrogens are a little bit positive, and they're all the same distance from the nucleus, and I can draw a circle that will capture all 4 hydrogens, or more appropriately, it's a sphere, right? This is these 3 on the bottom don't lie in the plane. So the corners of the tetrahedron lie on a sphere. So where is the center of positive charge? The center of positive charge is right here at the center of the molecule. And where's the center of local negative charge? It's on the carbon, because the carbon is the negative end of all of the bonds. So the centers of positive and negative charge for the entire molecule are co-located at the center of the molecule. So this means no net dipole moment. No net dipole moment for the molecule. So this is a nonpolar molecule. It's a nonpolar molecule consisting of polar bonds. Nonpolar molecule. So there's 2 ways that I can get a nonpolar molecule. One way is to have a homonuclear molecule, right? So homonuclear molecules axiomatically must be nonpolar, because they have equal sharing. So if I give you anything that's homonuclear, trivially, it's nonpolar. So you can look at things like H2, P4, S8. These things are all nonpolar. I don't care what their structures are. It doesn't matter. This one here is definitely polar. And then the last one here that we're looking at, the methane is nonpolar because we have spatially symmetric disposition of identical polar bonds. So spatially symmetric, that means there's a three-dimensional symmetry, spatially symmetric disposition of identical polar bonds. Leads to nonpolar molecule, because the centers of positive and negative charge are co-located. So now it's time to move on. So now I want to look at covalent bonding from energetic standpoint. I want to go back to energy level diagrams. All right, I want to go to energy level diagrams. Well, we've looked at energy level diagrams in the past for atoms, single atoms. But now what I want to do is build energy level diagrams for molecules. So for that, we're going to go back to the Schrödinger equation. I want energy level diagrams for molecules. Energy level diagrams for molecules. And for that, I'm going to call upon the Schrödinger equation. And we're not going to go through the quantum mechanics in mathematical detail. We're going to do quantum mechanics pictorially. Get a long way. And in particular, what I want to do with regard to the Schrödinger equation is to recognize that we can move from atomic orbitals to molecular orbitals by exploiting the fact that the Schrödinger equation is a linear equation, okay? Using the linearity property of the Schrödinger equation. All right, what do I mean by linearity? Well, I'm going to do just a little bit of math, just enough to make you sit up in your math classes and find out that there's some utility there. So here's what I mean. So let me talk about what the linearity principle is. So if I have some equation, f of x, y, and z, so it's a three-variable equation, and the equation is f of x, y, z goes as k1. Now, k1 could be a constant, it could be a function, it could be anything. And let's say that it has as its solution, the solution is S1. And then I got a second variant of this, x, y, z, and it equals k2. So it's the same function, but it equals k2 here. It could be a constant, could be something else. And it has as its solution S2. If this f x, y, z is a linear equation, then if I give you f of x, y, z equals k1 plus k2, you don't have to go and solve the equation with impunity. You can write that the solution is equal to S1 plus S2. And that doesn't hold if it's a nonlinear equation. You know, just put y equals x squared. And if I tell you y equals 1, y equals 2, and then I give you y equals 1 plus 2, it doesn't equal the sum of the solution to that. You can prove it to yourself. So this is the fact that superposition holds. You can superpose solutions and build a library. So superposition holds when you have a linear equation. And that's all we're going to use in order to make equations for the molecular orbital. So that way I can write that the wave function of a molecular orbital then is a linear combination of the atomic orbitals. That's all this is doing. This is setting the stage for, if you take quantum mechanics later, you'll go through this in gory detail, but I'm saying that you know enough now to appreciate that we can do what we're about to do. So that means I'm just going to sum the wave functions of the atomic orbitals. The atomic orbitals. In this case, I goes from 1 to 2, right? Because there's only 2 orbitals in a bond. And there'll be some prefactor here, a sub I times psi. Okay? And this whole business is called linear combination of atomic orbitals into molecular orbitals. So it's an SLI. It's a 6-letter initialization. You know, like FBI is a TLI. It's a 3-letter initialization. This is an SLI. In 3091, we go big. This is an SLI. 6-letter initialization. So we're going to do some examples here. And all you need to do in order to run the examples is use 2 ideas in LCAOM. Well, first of all, conservation of states, conservation of orbital states. And the second one is we're going to fill the newly created molecular orbitals according to the Aufbau principle. Fill MOs by Aufbau. If we do that, we're going to be in good shape. So let's take a look. So first thing I want to do is just rationalize this one here. H plus H goes to H2. I want to demonstrate that there's a rational basis for this. So what I'm going to do is make energy level diagrams. So there's an energy coordinate here. Energy goes up in the vertical direction, and out here is the 0. Out here is the 0. And what I'm going to draw for you is energy level diagrams for 2 atomic hydrogen gas atoms. So if this is the 0, we know that somewhere down here is the 1s, and I'm going to be complete my label. This is the 1s atomic orbital of hydrogen, and over here there's a 1s atomic orbital of atomic hydrogen. And furthermore, I've got an electron sitting in 1s. Now, these are at infinite separation. These are far apart, okay? Far, you know what that means. Far with quotation marks means that they're separate quantum systems. So I'm not violating the Pauli exclusion principle by having both of these electrons sitting in the ground state. So they both have the same set of quantum numbers, 1, 0, 0, a half. Both of them, same thing. Let's put it over here, 1, 0, 0, a half. So they're very, very far apart. Now, if I bring them close enough together to make the molecule H2, what happens is I'm going to violate the Pauli exclusion principle if I have both of these atomic orbitals at the same level. Because if I start filling them according to the Aufbau principle, I'm going to end up with more electrons than 2 at the same state. So what happens is this splits. One orbital ends up at a lower energy, and one orbital ends up at a higher energy than the ground state energy in the atom itself. And so now this is called the sigma 1s molecular orbital. Sigma 1s molecular orbital, and the one above it is called sigma star 1s molecular orbital. And sigma is at a lower energy, so if electrons populate this orbital, the system's energy will decrease and a bond will form. So this is called a bonding orbital. If electrons populate the upper orbital, they will raise the energy of the system, destabilizing it. And so this orbital, denoted with the star, is called antibonding. It's an antibonding orbital. So now I've got the energy level diagram for for molecular hydrogen. So now let's go and populate according to the Aufbau principle. I've got 2 electrons, and they go in spin up, spin down. And now you can see that this occupancy puts the electrons at lower energy than they were by being in the energy state of the atoms. And so I can argue that by this diagram, I haven't predicted anything, but I can use this diagram to rationalize that for this reaction, delta E is negative. And we know how negative it is. It's minus 435 kilojoules per mole. It's hugely negative. Minus 435 kilojoules per mole. All right. So that's good. In fact, I think I've got some pictures. So this is, you can go through the whole quantum mechanics, and just as is the case for single atoms, you can use the square of or rather the product of the wave function and its complex conjugate and so on, and make plots. Oh, by the way, this was just making the point that you can pull out the electronegativity off of the periodic table. It's given here. And the periodic table is pretty good, but obviously somebody got a little bit ahead of himself. They called this the first ionization potential, which is the potential you'd put across the plates in a gas discharge tube. But the unit is not the electron volt. If it's a potential, it's a volt. Somebody here that put this together seemed to think the electron volt is a unit of potential, and I want to make sure that nobody in this class believes that. So this is so you got to get a little bit of nail polish or something and cover up the little e there, okay? Or take the nail polish, paint over potential, and write first ionization energy, one or the other, but not this. All right. Oh, and this was a plot of percent ionic character. So you can see that the strongly covalent compounds down here have very, very low electronegativity differences and therefore very low ionic character. And way up here are the ionics. And in between is HF. It's almost at the cusp. But I can see can you see that there must be a mistake on this diagram? Because this thing's got a greater electronegativity difference than lithium iodide, and yet lithium iodide has a higher percent ionic character? How can this function zigzag like that? Something's wrong. So when you look at something, you go, hey, wait a minute. That doesn't make sense. So I go back, now I say, do I trust anything here? Trust but verify. Read critically. It's a good book, but you know, it's a big book and there's going to be some mistakes. All right, so here's some pictorial stuff of what we were just doing over here. So here are the 2 spherical 1s orbitals, and now they come closer and closer together, and they overlap, and this is what the shape of the sigma 1s orbital looks like. It's like an oval with the 2 nuclei inside. Here's taken from a different textbook. the overlap of 1s atomic, 1s atomic, and now here's the molecular orbital. Now, you can also look at what the shape of the antibonding orbital would be. This is what the shape of the antibonding orbital would be. It would have two lobes with a nodal plane in between. All right? Okay. This, I think this is taken from yet another book. Yeah. Oh, this is our book. All right, there we go. 1s, 1s, there we go. Hydrogen molecular orbitals. Now, look, suppose we do the same thing for helium. If we do the same thing for helium, helium starts with 2 electrons in 1s, and now it's going to have 4 electrons. 2 will go in the bonding, and 2 will go in the antibonding. And the 2 that go in the antibonding raise the energy of the system more than the 2 that go into bonding decrease the energy of the system. There's a net increase in energy, and this is the way you could rationalize that helium exists as the atom in the gas phase. You don't see He2 gas molecules. So using this energy level diagram, you can go through and rationalize. And I would never ask you to predict. I would say, fact, helium is found as the atomic species in the gas phase. With the use of energy level diagrams, rationalize. And that's what I'd expect you to do, to take this and show that the two are of different stability. One other point to make, the level of 1s, if I wanted to put helium on this board here, not to scale, but just roughly, where would helium 1s be relative to hydrogen 1s? Well, you got 3 choices. Same level, closer to 0 energy, or more negative. How do you think about the problem? What determines what this energy is? It's the electrostatic force of attraction. Is the electrostatic force of attraction on the 1s electron in helium greater than or less than it is in hydrogen? It's greater. So that means that the energy is going to be more negative. And so if I were to put over here helium, I'd put down here, this would be 1s atomic orbital for helium, and then we go through the analysis. And why does that come into play? Well, you might want to do a heteronuclear molecule. Suppose we wanted to do the bonding diagram for hydrogen fluoride. So we'd have hydrogen here, and the fluorine would be here, and all of the fluorine orbitals would be much lower, and then they'd combine to make the molecular orbitals. And I think there's some opportunities to practice that in the homework. Okay, let's do one more. How about lithium? Let's do lithium. I want to ask, is dilithium stable? Is dilithium stable? Li2. And this is all gas phase. Is dilithium stable? So I'll start off with, here's the zeros, the 0 of energy for infinite separation. So this will be a lithium gas atom, lithium gas atom, and this is the putative dilithium gas atom. We're going to figure out if it's stable or not. So it's going to have bonding and antibonding orbitals, and then this is the 1s, 2s, and this will be sigma 1s, sigma star 1s, and so on. And then we'll have sigma, 2s atomic orbital splitting into sigma and sigma star of 2s. And now lithium is 1s, 2, 2s1. So there's 1, 2, 3, and 1, 2, 3. And so now let's use the Hund rule. So I've got 4 electrons in the n equals 1 shell, and they populate in this manner. And then I've got 2 electrons that go only into the bonding orbital. And according to this, it appears that lithium-2 is favored over atomic lithium. And that, in fact, is the case. And so that applies to all of the alkali metals, because they all have the NS1 configuration. So when you're driving down the highway and you see those orangey yellow low-pressure sodium vapor lamps, what you're looking at is emission not from atomic sodium, but from Na2 vapor. And you've got the energy level diagram to convince yourself of that. So next time you see those, just smile, knowing that you're looking at disodium, not sodium, disodium. Okay. Well, so far we've only looked at single bonds. Now I want to look at multiple bonds, double and triple bonds. So let's look at nitrogen now, N2. Remember that gave us the triple bond. We had nitrogen 1, 2, 3, 4, 5. Second nitrogen 1, 2, 3, 4, 5. So in order to get octet stability, we had 3 pairs of electrons sharing, which then gives us a triple bond here. And so what's that going to look like? What's that going to look like pictorially? And the way to think about that is, first of all, these are all p orbitals, right? If we look at, this is 2s2, 2p3. So 2s, and these are the 2p orbitals. So I've got s is filled first, and then I've got the lone electrons in each of the p orbitals. And these things are shaped like figure 8, like figures 8. And the p orbital, this is the p atomic orbital, it has 2 lobes. Each of these zones is called lobe, same word as earlobe. And this zone in the middle, this one point in the middle, is called a node. It's called a node. And that's a site of 0 electron density. 0 electron density. And remember, the electron, even if it only has 1 electron here, the electron can be in either lobe, and it can move from lobe to lobe, even though it can never be at the nucleus. And how does it get from one lobe to the other while never crossing the nucleus, because it's never supposed to be in the nucleus? By behaving as a wave. The same way as you can have a jump rope and you can have a fixed point of 0 motion, yet you can transmit energy down the rope past a node. All right, so let's draw these things. I'm going to draw it like so. A word about how you draw. You have to use the right-hand rule. So when I put the coordinate system up, it's going to have to conform so that the thumb is x, and then you go y and z. And if you don't use the right-hand rule later on, if you get into electromagnetics, you start looking at forces and vectors, you're going to end up with things moving in the wrong direction. So we conform to the right-hand rule. And the other thing, and this is kind of nice, it's not mandatory, but chemists generally like to have atoms bond along the z-axis. So that means we start with the z-axis here, if I'm going to put my second nitrogen, have them bond on the z-axis. And so that means if z is in the plane of the board pointing to the right, then pointing up must be y, and then pointing into the board must be x. And so I'll have, here's my px orbital, then the py orbital, and the pz orbital. And the 3 of these are all symmetrically disposed around the nucleus. And next to it is the same kind of floral arrangement. So I'll start with px, py, and pz. And now these are going to come close together and overlap. So I want to figure out what those orbitals are going to look like. So let's start along the z-axis. The z-axis is the easy one. So I've got 2 of these things lying on their sides, like infinity signs. So we're going to do quantum mechanics pictorially. Why? Because it's a linear equation. So I can add pictorial. So this is 2pz of one of them and a 2pz of the other. And this is the nitrogen atomic orbital. Nitrogen atomic orbital. And I'm going to smear these things. And what are they going to look like? The nucleus is here. The nucleus is where I'm pointing indicating the dot. These 2 combine, very simply, it's going to look like this. So there's one nitrogen. Here's the other nitrogen. And what's this thing? This is electron density. And so this is our sigma bond. It looks a little bit different from the case of hydrogen, because hydrogen was the blending of 2 s orbitals, and s orbitals are spherically symmetric. In this case, we've got 2 lobes. But what's characteristic about this one and hydrogen? Hydrogen looked like this, remember? This was hydrogen. This was H2, and this was a sigma bond. The characteristic of a sigma bond is that when you start from one nucleus and you go to the other nucleus, you move through unbroken electron density. So there are no nodes, no holidays between the nitrogen nucleus on the left and the nitrogen nucleus on the right. There is a node here, but that's different. I can go from one nitrogen to the other with unbroken electron density. That's what makes this a sigma bond. I can go from one hydrogen to the other with unbroken electron density. That's what makes this a sigma bond. Okay, so that's good. So this thing here is going to be called sigma 2p molecular orbital. Sigma 2p molecular orbital. All right, and I think I've got the slide that shows this. There's some nice artwork. People really get excited about this. Okay, there's dilithium or dipotassium, disodium. Okay, so here we are. This is the smearing of 2pz atomic orbitals to make the sigma 2p bonding orbital. And there's, just for grins and chuckles, is what the anti-bonding would look like. But we don't care because it doesn't form. So what? Oh, this is the book. And you know what I'm going to say. I've got my little hobby horse here. I don't know why they change color on the lobes. Because when I look at that, it starts conjuring up to me the image that one electron stays in the blue lobe and one electron stays in the yellow lobe. Besides, I've seen them, and they're not different colors. They're the same color. Okay, good, good. All right, so now let's look at what happens when we blend off the z-axis. So let's blend the two py orbitals. See what that goes like. Okay, so let's do that one. And that one's going to look like this. We're going to start with, again, figure eights. But now they're side by side. They're lateral. So this is 2py atomic orbital, 2py atomic orbital. And we're going to blend them along the z-axis to give us, and I'm going to do this stylized, okay? So there are the two nitrogen nuclei. So I put the nuclei up. And I'm going to smear the upper lobes. So these two lobes are going to smear, and I'm going to get really stylized. I feel like it's France and it's the late 1800s. So there it is, all right? And I'm going to smear the two bottom ones, and it's going to look like this, right? So what do I have here? Now I have two lobes as before, right? But if I look at the second nucleus from the first nucleus, not only do I fail to have unbroken electron density, I have 0 electron density. See, this was a nodal point in the atom. With the two atoms together, the plane orthogonal to the board is a nodal plane. There's no electron density in the plane orthogonal to the board. Nodal plane. So this is definitely not a sigma bond. This is a pi bond. This is a pi bond. And it's characterized by smearing of atomic orbitals, just as the sigma bond is, but it has a nodal plane that separates the two lobes. Two lobes. And I think I've got some cartoon illustrations from other books here. Okay, this is from one book. This is good. They called it PX, I call it PY, but anyway, there it is. And I'd go further, and I'd say that if I were to slice this and look at it from this angle, you know, if we were to cut this and look from here, I'd venture that you'd see something that's sort of figure eight-ish that portrays that. Oh, here's our book. Bless them with their two colors, okay? But anyway, so there's what it looks like. That's the pi. That's the pi. So, and then the same thing happens with the x, all right? So this is going to be pi 2py. This is pi 2py, and it's a molecular orbital. And there's going to be a pi 2px, and it's going to blend front and back. So we can now make a catalog. So we're going to do quantum mechanics and pictures here, all right? So I know that S plus S must always make a sigma bond. There's no other way because I've got electron density all around. Let's do it pictorially. Okay? That's easy. And this is sigma. We know this has to be sigma. All right? What about something like HF, where the H is an S, and the F is going to have the one last electron missing in the p orbital. S plus p must give sigma always, because that's this cartoon. See, there's no way that when this smears with this, there's going to be 0 electron holidays from the hydrogen nucleus to the fluorine nucleus. So you're going to end up with something that looks like this. It starts around and gives you something that's going to be a little bit asymmetric. Okay? So this will also be a sigma. So I'll just put HF here as sort of prototypical of that. And then if I take P plus P axially, on axis, that also gives us a sigma. That also gives us a sigma, right? Because that's this one, the infinity signs. 2 infinity signs give us the, okay? And then finally, if we get P plus P longitudinally, so that will give us a pi bond, and that's the 88. 8 plus 8 gives me, and this is pi. So that's quantum mechanics. The math will follow. Math will follow. All right, so now what I want to do is go back to this energy level diagram and show how these energy level diagrams can work. All right. So here's the energy level diagram for nitrogen, N2. There's 2s, 2p, and the scaffolding is in place. There's the energy levels. All right, and here's the molecular orbitals, and here are the atomic orbitals. And now here they are occupied. So nitrogen has 1, 2, 3, 4, 5 according to the Hund rule. And here is the setup for the N2 molecule. So the 2 S's and the 2 S's go bonding, anti-bonding. Now I've got 3 plus 3 is 6, 2, 2, 2. Everything's paired. So we get the triple bond, 946 kilojoules per mole, an enormous energy in nitrogen. Enormous energy in nitrogen. Now let's keep going. Now let's look at oxygen. This is the scaffolding for oxygen and fluorine. And there's a little change here. A little change. I'm going to draw your attention to it. And you can't predict this. We would give you this. I would tell you what the energy sequence is of the energy levels. But look here carefully. You see in the case of nitrogen, the pi's lie below the sigma. In the case of oxygen and fluorine, the sigma lies below the pi's. These are tiny, tiny differences, but they're measurable. All right? Well, that's the little difference. Now let's see what happens. Actually, here's from our textbook, and it shows the sigma 2 pi x slowly meandering down, 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 and somewhere between nitrogen and oxygen, it crisscrosses. All right, so now let's fill oxygen. So oxygen is 2, 4, 5, 6. So 2 plus 2 is 4. There's the 2, 2, 2. And then these last ones go up into the anti-bonding. But look at the anti-bonding. We have, according to the Hund rule, not 2 electrons in the first orbital, but 1 and 1. So we end up with unpaired electrons in the anti-bonding orbital. So these offset the 3 pairs here, and so we end up with a double bond, and its energy is 498 kilojoules per mole, substantially less than nitrogen. And this energy level diagram rationalizes that. Okay? And then here's for fluorine. If you go to fluorine, it's the same scaffolding, only there's 2 more electrons. These are paired, and you have a single bond, 160 kilojoules per mole. Now, there's a property that we get from the fact that we have these unpaired electrons. I'm going back to oxygen now. We have unpaired electrons in the anti-bonding orbitals. We saw unpaired electrons. What did it do in the Stern-Gerlach experiment? Changed the magnetics substantially, right? We ended up with the splitting of the silver beam. So this will also have an impact. It has an impact known as paramagnetism. What's paramagnetism? It's shown in this little cartoon. If you have a substance here that's balanced and it is paramagnetic, if you engage the magnetic field will pull on a substance that's paramagnetic. And oxygen is paramagnetic, not only in the gas state, but it's paramagnetic as liquid. And here's an illustration from your textbook. You may have seen this and said, yeah, guys pouring liquid oxygen. Wow. No, look carefully now. The liquid oxygen, the boiling point of oxygen at 1 atmosphere pressure is 90 Kelvin. So room temperatures are substantially higher. This would be equivalent to taking water and putting it in an oven at about 300 degrees Celsius and watching it pour. It would still be liquid, but it would be liquid trying to boil. Why doesn't it all turn to gas? Because there's a time to heat everything. So this is sitting at 90 Kelvin. He's pouring it down, or she's pouring it down, and these are the jaws of a permanent magnet. And it's in a gravity field. It doesn't keep falling. It stops, and it continues to boil away, and as fast as you can pour it, it sits between the jaws of the magnet because it's paramagnetic. You can think of this as the liquid equivalent of iron filings. If I told you that these were iron filings, you'd say, yeah, the iron filings go and they stick to the magnet. That's what magnets do to iron filings. They do the same thing to liquid oxygen. And why? Because of this. This explains this. So we can do a lot with these primitive little diagrams. Do a lot. Okay. Well, let's do one more. I want to do one more of these things. I want to go to hybridized systems. So I want to go to a hybridized system, and I want to look at ethylene. I want to look at ethylene. C2H4 is ethylene. Okay, so if I told you, give me the Lewis structure of ethylene, you just start going according to the rules. So I'm going to have carbon, carbon, hydrogen, hydrogen. All right, and carbon has 1, 2, 3, 4 electrons. The hydrogen has 1 electron. I'm going to put the 1 electron from hydrogen. And then the other carbon over here, I'm going to give it dots, 1, 2, 3, 4. And then these hydrogens each have 1. And now let's see what I have here. These hydrogens are all isoelectronic with helium, so they're happy. And the carbon now has 2, let's see, what has he got? Yeah, carbon's happy, 2, 4, 6. Okay, good. So now carbon is happy as well. So what do we have here? This is equivalent to a carbon-carbon double bond. Carbon-carbon double bond. So what have I learned with the nitrogen example? What I learned with the nitrogen example was that if I want to make more than one bond, I have to have a combination of a sigma and a pi. You can only make one sigma bond because there's no room. Once you've got 0 electron density between the two nuclei, you're going to violate the Pauli exclusion principle if you have another orbital cutting through that same domain. So this means that multiple bonds require a mix of sigma and pi. Multiple bonds require a mix of sigma and pi. If you have a single bond, all you need is the sigma. All right? So let's go back to how we got the original hybridization. Remember, we started with carbon, with the box notation looking like this. Here's the 2s and the 2 p's, and we started with just native carbon off the periodic table, and we have this, just if we go according to the 2s2, 2p2. And then in order to get hybridization to rationalize methane, where we've got 4 equivalent bonds, in that case, we hybridized the s and all of the p's. We took the s and all 3 of the p's to make the sp3 hybrid orbitals, and then we were able to take these electrons and put them in one at a time, and then bring in the 4 hydrogens, and we end up with something that is symmetrically disposed in space, the carbon, hydrogens, and so on. So now I give to you ethylene. You say, well, how do I make ethylene? You say, well, gee, if I started with this sp3 thing, maybe I could bring another carbon over here, and I'd have 3 hydrogens sticking out. So there's my sigma bond, so I'm off to the races. This is good, but now I need to build a second bond. So I'm going to throw away a couple of hydrogens. So I'll throw this hydrogen away and this hydrogen away. So I'm going to have now C2H4. I'm almost there. The only problem is this orbital is sticking out this way, this orbital is sticking out this way, and I don't have the license to bend these orbitals and build a double bond because they're 109 degrees apart and they are inflexible and they won't bend. So this hybridization technique will not work as such to give me what I need to build ethylene. What do I need? If I'm going to build a sigma and a pi bond, I'm going to need to reserve one of the p orbitals so that it can still be available for lateral smearing. Because how do I make a pi orbital? I make a pi orbital with an 88. So I need to reserve a p orbital so that in both of the carbons, I still have this pi bonding capability. So what I'm going to do is, instead of taking the s and all 3 of the p's, I'm going to take the s and only 2 of the p's and reserve 1 of the p's to be sitting there for lateral smearing. So instead, what I'm going to do is this. So this is going to be an unmixed p, and this is going to take the s and not 3 p's, but only 2 p's, and this will be called sp2. This will be called sp2. And now what do I have? I've got 1, 2, 3. And how do I put 3 of these in space? They lie symmetrically in a plane at 120 degrees, and then this thing is normal to the plane of the board. It's sticking out. Actually, I should have maybe drawn it in perspective like this. Okay? And so now I've got the ability to put 2 of these together. This will give me my sigma, and then these 2 things lying on their side will smear with the lobes to give me the pi. And now that's what gives me the double bond. And here are the cartoons that show this. Oh, here I took this from an old textbook. It was a textbook I had when I was your age. It was just, I wrote great books. And then I flipped this around, see? I did all this just for you. So I took this one, I flipped the image around. So they're the sp2s, these are the unmixed p's, and you bring them close together, and bingo, there's the sigma. That's this one, p plus p axially. That gives me the sigma bond, and I smear those 2, and that gives me the pi. And there's ethylene. You put the hydrogens here, 1, 2, 3, 4, 2 carbons, ta-da. Isn't that cool? Here's from another book. This looks like a Boston traffic map, doesn't it? It's just crazy. Yeah. This is from our book. So they're showing you the, I don't know, so there's the sigmas and the pi's. Yeah, there we go. Okay. Good. More pictures. More pictures. More pictures. That's enough. Okay, I want to take 3 minutes at the end here and show you an example of electronegativity at the extreme. So if you take a look at the periodic table and look at a compound like sodium iodide, if I just told you sodium iodide, covalent or ionic, you'd say ionic, because you got something from the most metallic of the metals and something from the most non-metallic of the non-metals, and you're right. And the delta chi is 1.73, and the covalent character is high, and you end up with something that's very polar and so on. Now here's a very interesting one. If you compare cesium and gold, you get 1.75, which is greater than what it was for sodium and iodine. Now, no one would argue that sodium and iodine is covalent. You'd argue that's ionic. Well, by the same metric, cesium and gold is as ionic. The plot thickens. Cesium, if you melt it, it's a metal, liquid metal. If you melt gold, it's a liquid metal. But if you mix them in equal numbers, so you make an alloy of 50 mole percent cesium and 50 mole percent gold, and you've got a delta chi of 1.75, you've essentially made a cocktail with equal numbers of really good electron donors and really good electron acceptors. And guess what happens? Electron transfer. And the melt is not metallic. It turns clear and colorless, just as molten sodium iodide would be. It turns into a molten salt. So cesium gives its electron to gold, and gold becomes the negative gold ion. And what color is every ion? It's got stable octet configuration. It's got to be the same color as neon, argon, helium. They're clear and colorless. Big drop in electrical conductivity and a shift from electronic to ionic conduction. Metals have electronic conductivity. Ions, what do ionic liquids have? They have ionic conductivity. Here's some data from the literature. This is the log of the conductivity as a function of concentration. So here's pure cesium over here. Here's pure gold over here. This is 600 degrees C. So the line stops here because gold melts at about 1060. So gold is a solid beyond this alloy concentration. But you can see this is roughly what you'd get. All right? So electronic conductivity up here at about 10 to the 4 Siemens per, this is ohm reciprocal ohms, but Siemens per centimeter. And down here, this is a very low value, ionic conductivity. So this is a liquid metal, and this is a molten salt. And it all happens just when you get very, very close to 50-50. So you end up with something called cesium oride. And it's sorcery. You have one vial of liquid metal. You have a second vial of liquid metal. You pour them, and it turns clear and colorless, and the conductivity drops 3 orders of magnitude, all because of electron transfer due to this electronegativity difference. That's so cool. That is so cool. Okay, with that, I'll let you go. We'll see you on Friday.